I'm Hazel. I'm a third-year undergrad in Indiana, and I wrote a program synthesizer, and then I named it after a cat I found on Twitter. So let's take a look at what it does. So this needs no introduction for all of you, well, most of you, but How to Design Programs is a book that exists. It's a curriculum that involves these pedagogical subsets of the Racket language. I'm focusing on the first one, the beginning student language. We use it in Indiana for this course called C211, which people take and usually like it. And it emphasizes reasoning based on the design recipe, a formula, a certain signature, and test-driven design. We just talked a lot about the flaws of the non-prescriptive, of like going from prescriptive to non-prescriptive design recipes. I'm talking strictly about the prescriptive design recipes because I'm making a computer do it. So, the key observation of how to design programs is that we have this thing called the template, which is that we have a correspondence between the shape of our data definition and the shape of structural decomposition on that data definition. For example, if we have a structure date which has a year, a month, and a day, all of the functions that work with a date are going to take out the year, the month, and the day in some way. It might ignore some of them, but all of your functions are going to eventually look something like this. The same thing works for enumerations, where we introduce conditional. There you go. Where we introduce conditionals. So here we say that a traffic light is one of red, yellow, and green. And so we say, okay, if it's red, do this. If it's yellow, do this. If it's green, do this. This generalizes to more complex data definitions. Here we have a tree of dates, where a date is already a thing that we define. And we say that we check if it's a leaf, and if it's a node, then we know the left is a tree of dates, so we have to call the process working on that. If we say the date in the middle is a date, so we call process date on that, and the same to the right. So our design recipe says that we start with our data definitions, we write a signature and purpose statement for our function, we write some unit tests that ideally cover our specification reasonably well. We write our template. Here, I'm making a function called multiply by, which multiplies every element in the list by n. So we follow the template for our list of numbers. We write our function definition using some ingenuity to fill in the blanks, so generally not that much. And then we run our tests, and they pass, and everybody is happy. Or maybe they're not. Up to them. So, the key observation here is that our three things up here, our data definitions, signature and purpose statement, and unit tests, are things that we give as this kind of input to the design recipe. We say that these are going to dictate what our function should be, and our template and tests, and to some extent the definition, are things that fall out as a result. So the key observation that my synthesis work is trying to do is turn these steps 4 through 6 of the design recipe into a closed loop. So it continues trying to refine that solution until it finds something that works based on steps 1 through 3 as input. Here, I'm going to be synthesizing a function depth, which takes a tree of numbers with no element on the leaves, and then a left, a value, and a right for the node. And it's going to compute the max depth of the tree. We start off with this function. Tree is known to be a tree of numbers, and we have this hole that's in the shape of a number.
Question?
Yeah?
Is that thing where it says brace ... number, is that literally the syntax of your tool?
No.
Is this a thing that you're doing in the slide?
This is a slide trick.
Okay.
So the input to the tool is literally just define depth tree ... plus all of the inputs. It actually parses comments, which is awful, but like we would do anything rather than run a type. So here we start off with our initial environment where we say, okay, we have all of this stuff which is built in. I'm not going to go into that, but since say we have max in here, add 1 in here, plus in here with their respective signatures. And we also have this variable called tree at our environment, which is a tree of numbers. So what's a cool number? Any examples?
5.
Awesome. I used 0. Anyway, this example sucks. But using my incredibly very intelligent synthesis strategy, it's going to try this. and it's going to fail the tests. So that's one thing that we can do, is guess a number. This number is bad and we don't like it, so let's try something else. We can try doing a bunch of other things. We could try plugging in a function and then trying to synthesize its arguments. But the most interesting pass is the one where we try to synthesize the template. Here, we dispatch on what kind of thing it is, so we generate the template from our data definition, and we say, oh, it's either a leaf or a node because this is an enumeration. Since in our first thing here, we have an environment that says we have a tree, which is a tree of numbers. Here we still have a tree that's a tree of numbers, but because we know that this is a node, and because the node case has other things in it, we actually add those things to the environment. So we say we have the left and the right, which are a tree of numbers. We have a value, which is a tree of numbers. And because we're doing recursion here, because we have our tree of numbers referring to a tree of numbers, we add the recursive calls themselves to our environment. This is why we always generate like structurally recursive terminating functions. We're straight up following the template. So we could also guess an application. So we could say, oh, add1 is a function from number to number. Let's try that. That would be cool. And then we have another number-shaped fold that we need to plug. We keep doing this for a while, and eventually we end at this solution, where our leaf returns 0 and our node returns add one of max to the left and the right.
After a while?
Currently it's a little bit less than 30 seconds. It's way better for smaller inputs. Like, it can do length, it can do products, like that.
More interesting than time is trials.
Yeah.
Like, how many iterations of this does it take to get to that?
Yeah.
I was wondering how big the standard library that's used.
I have like 6 numeric primitives and a lot of string primitives, but the string primitives are filtered out, so it doesn't even try and guess those, so it's not actually running into anything beyond an initial filter. So, anyway. So, actually implementing this thing. So anyway, I read this cool paper. You should read that one instead of any paper that I'm kidding. But this is a paper by Peter Michael Nocera and Steve Stounswick about the myth program synthesizer. Yeah?
I'm just wondering, in the example, could it have synthesized a function that doesn't recur?
Yes. It could have hypothetically synthesized a function that doesn't recur. This is the smallest example for these inputs, but like, let's say you were to delete like this test, and you just said, oh, it's this if it's leaf, it's this if it's node. It's going to say, oh, if it's leaf, it's 0, and if it's node, it's 1, which is very useful. Yeah.
Does it use any kind of heuristic to guide this, or is it sort of just right for its search?
More on that later. Not yet.
Okay.
I'm planning on changing that because that would make it significantly faster. It's just I'm trying to also figure out what I want to actually do with this thing, which is hard. So this synthesis tool is extremely performant, but has a lot of constraints that make it not quite what we want. Namely, I know beginning student is a very simpler language, but the thing that Myth synthesizes for is arguably even simpler, insofar that it doesn't have any non-inductive types that are interesting. So we define numbers in the piano sense, and then we turn them back into piano numbers. And we also don't have much in the way of constants. So like the stutter function here doesn't actually refer to any number like 0 or 3 or whatever. But when we're doing stuff for HtDP, obviously we care about that kind of thing. We want to be able to synthesize, say, something that adds 3 to every element of a list. So this is the main difference. We have non-inductive data. We have stuff like strings. We have constants. We have a couple of signatures that don't behave quite like your standard types. Like in 211, we introduce intervals, etc., which you would need a very expressive type system to talk about. And also we have a large collection of primitives. 6 is pretty large. So our core algorithm basically generates this tree of refinements, where we say, we start off with a number, and then we can do plus, We can introduce a template. There are a bunch of different things that we can do to turn this number hole into something else. We could try guessing functions. We could try guessing other stuff. And eventually we end at our final solution. So we then do breadth first search on this tree, and the first thing to pop out that satisfies the test is what we work with. These refinements correspond to 5 things right now. I can think of at least 2 more that I want to implement, but hey. Introduce lambda, which is decidedly a misnomer because we don't have lambdas in beginning students, meaning this is actually only called once at the top level. Is for any signature that's for x to y, introduce a function definition. That's the easy one. Anyway, guess var says if we have a matching variable or interesting expression like depth of node left, for example, plug the hole with that thing. Guess const guesses a known constant or one from a unit test. For example, if we want to be able to synthesize factorial, we always need to be able to guess 0 or 1 or whatever for a number, etc. Or we read through all the unit tests and we say, oh, this number shows up in the unit test. Let's try that. That might be useful in the most naive way possible. Guess app, which says if we have a function from x to y, and we have a hole that's in the shape of an x, let's make a hole that's in the shape of a y, and then wrap around it. And finally, the interesting one is guess template, where if we have some kind of inductive x in the environment, guess its template, and then extend the environment with any recursion that's necessary. Like as we added depth of node left and depth of node right in the example. So what do we actually want to do with this thing? Great question. I'll get back to you on that one. So what's this good for? First off, we have a lot of auto-grading scripts that we've been writing in C211. They were made by a crack team of undergraduates in the spring, and a lot of them are really weird looking. So as an example, here we have this function landRacket, which takes a rocket and draws a little animation of it going down the bottom of the screen. So the problem is that this is basically impossible to test reasonably. People could do a lot of different functions, and people could do a lot of different sprites, and nobody has any idea what that would look like in an autograder. And we don't want to mandate that we do actual image comparison, because that would be bad. So we say, these particular inputs have to return an image, and also it has to change between these 2 times and not change between these 2 times. This is obviously not as exhaustive as you would like. So what we would like to do is say that this function follows a certain shape. So basically, if we run this tool with a kind of crib, if we delete something from student code and then put it back in, and the name just to generate it, we know it's correct. In addition, this is questionably useful, but we can use it to determine inconsistent sets of unit tests. So if you have a set of tests that you try to put in and then the synthesizer blows up, either I have made a horrible mistake, or your tests are bad. Finally, we can also use this to, actually wait, I just mentioned that. So, making it faster. With regards to heuristics, I've been thinking about using Dijkstra's algorithm instead of BFS. This would be much faster in my mind, especially because there are certain primitives that show up way more than others. For example, we probably care about add1 way more than we care about max. One of the other things that I want to be able to do is remove unit tests for consideration set of conditionals. So in the previous example, we knew that depth of make leaf would have to be 0. There is reasonably nothing else it could be because there's no other things that could really go in that hole that would satisfy those tests. So what we could do is prune down the unit tests and then only check the ones that handle the leaf case. Finally, Myth has this implementation of refinement trees where we have basically, we enumerate all of the possible shapes that this function could take and then cache it and plug the holes. This would also be a significant performance improvement. We also can't really apply this algorithm for our arithmetic and string functions. As an example, this days to year function, where we take the days since the 1st of January and return the year, requires a lot of complex arithmetic, and this is actually harder than recursion. I keep trying to tell my students that, but they don't believe me. And so calling another synthesizer specifically for these tasks, like Rosette or Z3 or whatever, would work. So this is one of the refinements that I'm working on in the sidelines, is trying to do that get stuff like Fahrenheit to Celsius, etc. And that would ideally be the first thing that we try, is trying to synthesize an arithmetic expression, and if that doesn't work, start doing recursion. We also need some way to call this. This is an older iteration when I was still doing a gen sim, so it looks kind of funky. I'm not doing that anymore. So we provide a very basic API that actually parses all of the comments from the student files. So it will literally read off the definition of a tree of numbers here. And we also made a DrRacket quick script that runs the synthesizer. And it works very well as of yesterday. So, some examples. That is the wrong desk. So here is the simplest function that I can think of. This literally just adds 3 to the input. We go to scripts or in Bingus and just does it. That's not particularly interesting, so let's think about the one recursive structure that some people coming out of 211 actually managed to understand, lists. So here we want to multiply the elements of an input list. So we run Bingus and takes a second and does it. Okay. Here's more examples. This one in particular is very fast because it literally doesn't involve the first. Yeah?
Could you go back up to add 3? If 3 is, if you replace the test case add 3 is 6 with add 3 5 is 8, what will it generate?
It won't. That's why I'm planning on pulling in Z3, because otherwise it would literally not know that the number 3 existed, because it's not in like the set of like known constants.
Would it get to add 1, add 1, add 1?
Actually, wait. It might.
Let's try it.
Yeah, let's find out. Add 3, 5 is 8. I'm gonna wait to find out. I didn't even know that would work. Nice one. So that's cool. Thanks for teaching me about my own tool. So anyway, life is also pretty fast. So you press that, and it just does it. Again, this one's even simpler because we just ignore the first, so it never has to guess applications in the environment, which increases the depth of the tree. In 211, we don't actually start off with lists. We start off with simplest structures like this one. So here we have this thing we call a nesting doll. This is like the first thing that we give to students about recursion, where we basically make a homomorphism across dolls, I can't words, where we take a doll and we return a doll that's green and has the same nesting depth. So you press here, and it'll take a second to think, and there you go. So here it actually read the doll data definition, and returns a small doll with green if it's small, and otherwise it makes it larger and then does the recursive call. This also works for, this is kind of the 211 preliminary to lists, is we have a bunch of numbers, which is like a list, except we don't use cons. And if you did that, then it takes a little bit more time because that's to figure out stuff in the environment, but there you go. Same deal. Yeah?
Why does the code keep disappearing?
Because I keep pressing Control-Z. I don't know why I'm doing that. It doesn't disappear unless I press Control-Z. Yeah?
Is it always doing it from left to right?
What do you mean?
So how are you processing first press?
It doesn't necessarily do it from left to right. It's stored in a hash table, and the ordering of those things is non-deterministic. So it's actually guessing them in order when it reasonably shouldn't, but I don't have a good ordering to put on it right now. So yeah, that's one of the things in the test suite that I had to deal with, is sometimes it'll generate product of some rest and some first. and sometimes it'll generate some first times product of some rest. And I need to be able to say that those two things are the same because times is commutative, but I don't want to tell my test suite that times is commutative, and yeah, I worked on that for like a week. Anyway. And this generalizes to more complicated recursive structures. Yeah.
But you can solve your problem quite easily by making that data definition recursive.
Wait, which data definition?
The one that of the range of numbers, right?
I mean, this is a recursive data definition. Like, it's not guessing the template outright. It's putting the stuff from the template into the environment.
But there's a hash table involved somewhere.
Yeah.
Keys to the hash table are random, and that's why
Yeah.
sometimes it's in
What
wild.
I meant is that if you make your range of numbers 2 numbers instead of 1, then you could have a sub-range of 2 numbers.
Right. Okay. Anyway. And this also generalizes to more complicated structures. Here we multiply a tree. I'm a really big fan of multiplication, as you can see. It takes a little bit longer, but here we multiply the left by the right. And this is the example which I said takes about 30 seconds, so everybody buckle up. But if we run it, we're going to be here for a while, so I'm willing to field any more questions in that time. But
Is it faster than the projector?
yeah.
Here's another question along the lines of what happens if you change the program subtly. And I was wondering about if the student writes the kind of classic incorrect test cases for product, but it was 0 in the empty case, but then correctly put the product in all the non-empty cases.
That will probably, like, I am 90% sure that would just fail to synthesize. Because I can't think of a function that would do that. Anyway, there's depth. But
yeah, so perhaps this is future work, but this seems to cover structural recursion pretty well.
yes.
But generative recursion, not at all.
Yes. Generative recursion is hard. So one of the things that we do in 2.11, which is a little bit interesting, and I don't believe comes straight out of the HtDP book, is we have like this generative recursive function that generates this specific data definition. Like for merge sort, we generate a merge tree, and then we have this thing called merge tree result that then turns that into it. So like composition of a catamorphism and anamorphism or whatever. If you know what those words mean. If you don't, it's not important. But looking into that, it could definitely make it more viable for a synthesis strategy to pick that up. But at the same time, that would probably be like a completely different algorithm than what I'm doing right now. Yeah.
I'm kind of curious how this fits into the curriculum. So are students like running this as they're working on homework assignments or what? Because I know that professors a lot of the time are a little bit hesitant to give students tools that do work for them.
Yeah, no, we just give our students code. I'm kidding. This is something that I literally had a meeting about yesterday, is to try and figure out where to fit this in. Again, I think it could be useful for auto-grading for instructor purposes and to really show like the benefits of the design recipe to students. Because, I mean, the ultimate goal of this thing is to specify sort and get insertion sort out of it, because that is the structurally recursive algorithm for that. Mm-hmm. And if we can do that, that will be really great to show off. So,
Can you get it to generate the program in steps? So, like, it can explain to students, okay, you've got a program on a list, so the first thing it does is make the cons, and it would just make just the con part and have the inner branches stuff. You know, like, to kind of show that, like, the template is a thing that you fill in gradually.
no, but I could do that in 2 hours like that. That's just like taking the DFS and running backwards.
So for your like tests, do you ever run into problems where it's like they have a really trivial answer that it could be, and then they can't figure out why it's giving a trivial result? Or like if they just say, oh, I want to increment something, and then it gives like a silly answer that's like...
Yeah, so that's a thing, is this thing is really good at being maliciously compliant. If you give it a set of like 2 tests for a recursive data definition, it'll just get like Like, if it's a leaf, return 0, otherwise return 1. I am very smart. But I also have thought about that as a way to gauge when your function is underspecified. Like, if a student gave me the set of 2 tests, I would say they need to write more examples and they're going to get the wrong answer. So, if we compare this and see if it generates a good solution, we can also reasonably say that the set of tests the student has written is a good spec. And like, as we're going into an era where we have like way more tools that can generate this kind of stuff, and a lot of the code you're getting is reasonably based on Stack Overflow, this is a good example to say a lot of these tools that you're going to be using are going to suck, and you need to understand when the code that you're pulling from somewhere else is actually good. Yeah.
You kind of pulled the rug out from me. I was going to ask if you could use, in terms of use in education, this seems like a very useful tool for teaching students and giving feedback immediately to them on how to write good tests, like good lists of tests.
Yes, that is the primary thing. This is good at detecting inconsistent tests, and it's good at saying when your tests are undercovering, because it will overfit. Like, it is almost designed to overfit with the algorithm that you currently have.
Yeah, I think you can be even more explicit than that by, after discovering a solution, continue running the algorithm to see if there is another solution. And if that is, then you know that it's underspecified.
Yeah.
What kind of signatures do you support? Like, could it synthesize math? Like, if you just put X's and Y's?
It doesn't do polymorphism, no. Although, again, I don't think that would be the worst thing in the world to synthesize. But this is currently strictly for beginning students, not intermediate students, where we introduce higher order functional abstractions.
How lenient is the parsing?
Good enough to handle student code on the actual autograder, despite the fact that a lot of people complain about it every semester. But yeah.
I seem to remember net requiring trace complete examples.
This doesn't. There isn't. It's more that this is inspired by Myth. It's not using the core Myth algorithm, so it doesn't require trace completeness. It's also just in general a lot more naive than Myth, which is why I'm honestly surprised that it works as well as it does.
One thing to note here is that the reason it doesn't need trace complete examples, one, because it generates recursive calls based on structure of the data, and two, because it does not try to reduce the space of tests based on the to narrow down that it's looking at and use the test. It merely uses the tests as a filter.
Right. Narrowing the space of tests as we continue to refine the program is something that literally I have support for in the structure that I have written. It just right now it's literally a constant because I haven't implemented changing it yet. But yeah. Anyway, I wanted to put the stupid cat that I found on Twitter in the slides. I didn't have a good place to put it, so it's on the last one. Anyway, thank you.